So thanks for inviting me. Greetings from Puerto Rico. Here it's sunny. I assume you guys are in the winter, so warm regards from here. So I will talk a little bit about this new sort of singularities that appear in the last 10 years or so from Hodge theoretic considerations, and they are used in various problems in deformation theory and birational geometry and so on. These are the higher singularities, higher versions of rational and Dubois singularities. They are supposed to interpolate, they are supposed to be mild singularities, interpolating between the classical notions of rational and Dubois and smooth. And from their introduction, there were many attempts to characterize them in terms of other more manageable invariants. So what I will try to do today is to try to understand this kind of singularities in terms of characteristic classes coming from more classical singularity theory. All right, so let me start with the background classical stuff that I assume most of you are familiar with, the notions of rational and Dubois singularities, and then I will say what the higher versions are. These are natural generalizations. So rational singularities were already introduced by Artin and Kempf in the 60s or 70s. And the definition is what we learn, for example, in a basic algebraic geometry course. So an algebraic variety has rational singularities if for any or some proper birational map to our variety, so for example, a resolution, well, the domain should be smooth. So for example, a resolution, then the push forward of the structure sheaf from the resolution to the variety you started with is a sheaf. In other words, it's just the structure sheaf on the base. Examples, well, of course, smooth varieties have all kinds of singularities you like. In particular, they have rational singularities, but one can go the other way also. In the case of curves, rational singularities imply smoothness, so you don't really impose any conditions here. Of course, quotient singularities are rational, as we know, and perhaps a larger class of rational singularities, it consists of toric varieties. So toric varieties, of course, in the simplicial case, for example, they have quotient singularities, but non-simplicial case is more general. Okay. Then to define the notion of Dubois singularities, I have to remind you of the two ways of extending the de Rham complex to the singular setting. So one way to do it is by looking at Keller differentials. This is just like the classical de Rham complex. For example, for a hypersurface, this is easy to define, just using the one form defined by the function defining the hypersurface. But there is a more interesting complex called the Dubois complex, introduced by Dubois, I guess, in the early 1980s, which is constructed using hyperresolutions. So this definition takes too much space to put on a slide, and I'm not really gonna, this is a very complicated object. I'm not really gonna work with it, except that I will work with its graded pieces. So that's what we'll be mainly interested in. But for now, let me just say that there is a natural morphism of filtered complexes between these two notions of de Rham, generalizations of de Rham complexes. And of course, in the smooth case, you get the quasi-isomorphism. So in the smooth case, you just get the classical de Rham complex from both notions. All right, so what we'll be interested in are these graded pieces of the Dubois complex, appropriately shifted. So this shift, don't worry too much, it's just a cohomological shift to place the cohomologies of these graded pieces of the Dubois complex in the right cohomological index. But what's good about these things is that they have coherent cohomology. So these are complexes, unlike the case of Kähler differentials, where the graded pieces are sheaves. In the Dubois context, these are complexes and they have coherent cohomology. Now, as I said, these are difficult to compute in general, but there are some, well, first of all, of course, I should say that since they were defined in terms of hyperresolutions, these graded Dubois pieces, well, to be useful, they should be independent of the choice of hyperresolution, and this is indeed the case. It was shown by Deligne and Dubois. And as easy examples, of course, if you work in the smooth case, as I said, this Dubois complex, the one up here, is just the classical de Rham with the stupid filtration, and its graded pieces are just the sheaves of holomorphic forms, of P forms in this case. So in the smooth case, the P Dubois complex is nothing but the P holomorphic form, sheaf of holomorphic form, so they are sheaves. And there is also another situation when they are sheaves, and that's in the case of quotients or toroidal singularities. In that case, what you get are these Zariski sheaves. So you take holomorphic forms on the regular part of the variety and you push it forward into the ambient variety. So what you get are called the Zariski sheaves of P forms, and they coincide in this case with the P Dubois complex. So I should let me say that I don't really see who's on the screen or hands or comments. So if you have a question, just feel free to open the microphone and interrupt me, because I think that's the easiest way to communicate. Okay. So what I'm trying to do here now, I'm trying to define Dubois singularities, and these are defined through this Dubois complex, which I put on this slide. And in fact, to define Dubois singularities, you only need the zeroth Dubois complex, so omega 0, which is just the structure sheaf. Well, sorry, it's not a structure sheaf. We want it to be the structure sheaf. That's the definition of the Dubois singularity. So this is the definition on the next page. So the Dubois singularities are defined as those for which the structure sheaf, which is the GR0 piece of the Kähler differentials, coincides with the zeroth piece of the Dubois complex. Okay. So this was a definition introduced by Steenbrink. And again, I should get back to the previous slide. So we had this filtered morphism of complexes. On the left, you have the Kähler differentials or the de Rham complex. On the right, you have the Dubois complex. You take graded pieces, you get induced maps on the graded pieces. And in degree 0, on the left, you get a structure sheaf. And on the right, you get this zeroth Dubois complex. If these guys are quasi-isomorphic, then the variety X is called a Dubois variety. It has Dubois singularities. Okay, so this is the definition I put here. Now you can imagine how this would be generalized to higher singularities, right? I could simply ask for more of these graded pieces of the two complexes to be quasi-isomorphic. And in fact, that's the definition. We'll get to that in a minute. But let me just say that it turns out that these Dubois singularities are a larger class than rational. So rational singularities are Dubois, and this was proved by Kolar and Kovacs. And of course, Saito had something to do with this, and Steenbrink. But on the other hand, it is a strictly larger class than rational singularities, as I'll show in the next example. But first, let me say the nodal cubic in CP2. So this is what you get by degenerating, for example, elliptic curves. So it's like the pinch torus. This has Dubois singularities. On the other hand, the cuspidal cubic does not. And in fact, it's very easy. You'll see in a minute, all these Brieskorn type singularities are completely characterized in terms of what level of Duboisness or rationality they have. I'll give you the formula on the next slides. But let me also give you this situation here that cusp singularities of a surface now, not of a curve, they are Dubois, but they are not rational. So this shows that the class of Dubois is strictly larger than the class of rational singularities. So these are classical notions of singularities from the 80s, and recently studying families, the generations, and or birational geometry like the low canonical threshold and the minimal exponent, people came up with higher generalizations of these notions. So this is what I'm going to put on the next slide. So this higher Dubois singularities, or if you like, K Dubois singularities for any non-negative integer K, they are defined simply by asking that the graded pieces of the de Rham complex, or the complex of Kähler differentials on one hand, and the Pith Dubois complex, which was the graded piece of the Dubois complex, on the other hand, are isomorphic up to level K. Right? So this is just the map induced by the filtered morphism between the two notions of the Rham complexes in the singular setting, and we're simply asking for these things to be more and more isomorphic at a higher and higher level. So now, of course, in the zero, if P is zero, you simply recover the definition that we had earlier for Dubois, right? So omega zero is just the structure sheaf, and on the other hand, we had the zeroth Dubois complex. And of course, if you are K Dubois, so if these graded pieces are isomorphic up to level K, of course, you have K minus 1 Dubois and so on, right? So all the lower levels of quasi-isomorphisms are included in this definition. So this is a layer of singularities, and we'll see, well, maybe we'll not see today. I think I forgot to put it on the slide, that you may wonder how far I can go with this Duboisness, how high I can go. And well, at some point you end up with something smooth, right? So this will be the upshot of what you'll see in the results I discussed today. Also, the ones I worked on are the ones that, I should say, these are introduced by two different groups, this higher Dubois singularities, Jung, Kim, Saito, and Yoon. So this was one direction, and the other one was by Mustaza, Olano, Popa, and Vitashek. Olano is one of the collaborators of this work I describe here. And now I should also say that since I started with rational singularities, I should also say that there is, of course, a higher rational singularity notion, and this was introduced by Friedman and Laza around the same time for different purposes. They were the ones looking at the generations of Calabi-Yau's. And here, the definition is very similar to what you have in the case of rational singularities. So in this case, you take a log resolution of singularities. So this means that this divisor sitting above the singularities of X is a simple normal crossing divisor. And then you have K rational singularities if pushing down the log P forms from the resolution gives you the de Rham forms on the space on the base, right? So if you like, what this says is that this derived push forward. So this is a complex of sheaves a priori, but K rational singularities require that these are in fact sheaves, right, up to level K. So they are isomorphic to this de Rham sheaves. All right, again, K rational means quasi-isomorphisms up to level K. And if you do K is equal to 0, then you get just the classical notion of rational singularities. Just plug in 0 here, you get the previous definition. And the same story, right? You have levels, I didn't write it here, so K rational implies K minus 1 rational and so on. All right, so these are the definitions. The definitions themselves do not seem to have to do much with Hash theory unless you recall how the Hash structures were computed on a, let's say, smooth projective variety in terms of this log, in terms of the sheaves of holomorphic forms. So maybe let me give you an example. sorry, I just got up, so. But I promised I'll give you an example. So let me give you an example in the case of hypersurfaces, because these are the ones that are better and best understood before moving to local complete intersections. And then I'll describe some general results in the case of local complete intersections. So let's take the classical Briscorn type singularity. So we have this sums of monomials in distinct variables with exponents integers at least 2, and the hypersurface is defined by such a polynomial. Then K Dubois is characterized completely in terms of the sums of reciprocals of the exponents being greater or equal than K plus 1, and K rationality is equivalent to something similar, but the inequality is strict. So of course, now you can create any sorts of K Dubois and K rational, or which is one, which is not the other, and so on, right? So why this is true, what I stated here in an example, I'm hiding a lot. This has to do with what I'll mention later on, the minimal exponent. So this is a root of the Bernstein-Sato polynomial associated to f, and this formula, in fact, holds for a formula of this sort, holds for any weighted homogeneous singularity, and this is a calculation done by Saito. So now this K Dubois and K rationality as notions are completely characterized by properties of the minimal exponent, and what I'm calculating here on the right, this sum of reciprocals of exponents is just the minimal exponent. I'll get to this later on, but for hypersurfaces, as I said, everything is quite well understood. We have more issues moving beyond hypersurfaces or beyond complete intersections. All right. Here is another example which says that you can have rational singularities which are not one rational. So these are, for example, the toric situation. I told you toric varieties have rational singularities, but they are not one rational. Okay, quotient singularity is also the same situation. All right, so here are some general examples, at least in the case, general results, at least in the case of locally complete intersections, relations between these higher Dubois and higher rational singularities. I told you that rational implies Dubois, so you'd expect, for example, K rational implies K Dubois, and in fact, this is true. This was proved in 2 different papers, one by Mustatse-Popa, the other one by Friedman-Laza. So this is just a generalization for arbitrary levels of rationality implying Dubois. But then, of course, there is a relation going backwards. And this is K Dubois implies K minus 1 rational. So I told you earlier that K rational, of course, implies K minus 1 rational by definition. But in between K rational and K minus 1 rational, we can stick K Dubois. So this is in these inclusions, right? So now, the notions I gave you for higher Dubois and higher rational singularities did not involve local complete intersections. On the other hand, this second statement here is known not to hold away from the local complete intersection situation. So as a result, people are trying now to adjust the definitions of these notions beyond local complete intersections so that such an implication is still true. This is desirable to have. All right, so what I'll be doing here is I'll try to give you some characterization of K rationality and K Dubois for local complete intersections in terms of suitable characteristic classes for singular varieties. So this is what I'm doing for a living, characteristic classes are part of.
Excuse me.
Yes, go ahead.
Just a question. So, according to results A, B, if I mean more precisely the item B, you are saying that if X is K double R, it is K minus 1, but you are not able to get has a K rational, only K minus 1 rational.
No, yeah, it's not K rational because these are not equivalent, right? So
yeah. Yeah, because
So I told you K-Dubois
yeah,
is a
so
strictly larger class than K-Dubois. K-Dubois
yeah,
is a
so
strictly larger class than K-rational.
oh, I see, I see. But what you should add to get a characterization in such a case?
Oh, this is a very good question. So there is something about the intersection cohomology complex.
Oh, all right.
So
Okay, okay.
this is actually so if you look here, right? So we have this kind of K-Dubois and K-rationality. This example I gave you here, you see that the difference is inequality. I mean, greater or equal
Right,
versus
right.
3, and the actual. I mean, to go the other way, you have to impose an extra
Right,
condition.
right.
And this comes from looking at. I'll say in a minute. I mean, the best way to look at the singularities is through Harsh theory, right? So I mentioned Saito and his mixed-Hodge modules. You have underlying filtered D modules for these mixed-Hodge modules, and you take their graded RAM complexes. If you start with an IC intersection cohomology complex, looking at the graded pieces or studying the graded pieces of this, the RAM for the IC complex is what detects the difference between these two notions. And this is something that other people have done, including this my collaborators, Dirks and Olano. So they have a paper recently with other collaborators, or they actually tell you exactly what the difference between these two. In fact, you'll see this also in our paper. So there is something for hypersurfaces. This is very easy to see from the vanishing cycles and what is called the V-filtration. These are notions coming from Harsh theory. But for local complete intersections, it's a little bit more complicated. But still,
Okay,
the
okay.
IC complex comes into play. These are studied, these are well studied, and they're understood at least at the conceptual level. I mean, of course, doing calculations is usually not very easy, especially as you go beyond the hypersurface case. But the key point here is that K-Dubois is strictly larger than K-rational, and if you want, you can characterize K-Dubois as being K-rational plus something else. This is the something is missing here to make it to K. Sorry, the other way. Something is missing to make an equivalence here, right? And this has to do with this intersection cohomology complex, which is one of the key ingredients for studying singularities, singular varieties. This is not something what I'm going to say here. This is it's been already worked out by other people. So I'll focus now on characteristic classes. This is what I'm trying to do. So these characteristic classes come from what I just mentioned, vanishing cycles. And I think from the results I'll describe, you'll see exactly the difference between K-rational and K-Dubois. You'll see exactly what's missing. There is always a missing piece in this. My results are characterizations of K-Dubois and K-rationality in terms of vanishing of certain pieces of characteristic classes. And an extra vanishing would give you an equivalence between the two notions. All right, so let me define the spectral classes. So these are, I'll define first the general concept. These are things introduced quite a while back by myself and Schurman and Saito. So we have an algebraic variety in general. We work with mixed-Hodge modules. These are typically complicated objects, but they are very powerful. They give us Harsh theory more or less for free once you digest the formalism. Let me denote by HI either the Borel-Moore homology or the Chow homology. Either is fine. And then I'll make this definition precise on the next slide. We have this what we call spectral Hirzebruch class transformations. So these are defined on the Grothendieck group of monodromic mixed-Hodge modules. So these are mixed-Hodge modules with a finite order automorphism here. So I'll give you the main example in a minute, and this is in fact what's going to define the classes characterizing K-Dubois and K-rationality. And of course, what you end up with is besides homology, you'll end up with some parameters some variable raised to some fractional powers, some rational powers, given by the order of the various automorphisms you play with. So here, if E is the order of automorphism, you'll get powers of 1 over E, Laurent polynomials in 1 over E. I'll make the definition clear on the next slide. So this, in fact, mimics the definition of the Hodge spectrum of Varchenko, Steinbrink, and Saito from the case of isolated singularities. So this is what, in the case of isolated singularities, in fact, this class reduces to the Hodge spectrum. So it is defined to reduce to the Hodge spectrum if the singularities are not too complicated. But otherwise, it may have components in higher homology groups. So here is the definition. So we work with, if you, well, typically you start with a smooth variety because you want to work with D modules. So mixed-Hodge modules on a smooth variety have a D module component, and they have a perverse component, perverse sheaf component, and there is a Riemann-Hilbert correspondence between the two. But for this definition, I only make use of the D module component. This is endowed already with a filtration which corresponds to the Hodge filtration on cohomology. So let me take a mixed-Hodge module with a finite order automorphism. Let's say the order of the automorphism is E. And what I'm doing now, I look at this D module with this automorphism acting on it, and I decompose it in eigenspaces. So these M lambdas are the pieces on which this finite order automorphism acts as multiplication by lambda. So this is like linear algebra, right? You have a vector space with a finite group acting on it. Take the eigen decomposition. Okay. Now, I mentioned already these words. To D modules, you associate the RAM complexes. So if you haven't seen this, so there is an induced filtration from the one of the mixed-Hodge modules. So you can think, for example, what the RAM complex would be for the structure sheaf. So the structure sheaf, you can think of it as a D module. You act on it. You act on functions by various operators. So D modules is this is the ring of differential operators acting on, I mean, you have the functions locally given by coordinates, and you have differential operators with respect to these coordinates. This is what defines this dx as a ring, and then you have a module over this ring of operators. And the de Rham complex for the structure sheaf O, on which you act by differential operators, right? You act on functions by various differential operators. The de Rham for the structure sheaf is just the classical de Rham complex, right? We're in the smooth context here. So the classical de Rham complex of the holomorphic forms. With the induced filtration, in the case of the structure sheaf, the filtration is the stupid filtration. So the graded pieces are just the sheaves of holomorphic forms. But in general, the graded pieces are of this induced filtration on the de Rham. They are complexes themselves with coherent cohomology. So we take those graded pieces in the Grothendieck group of coherent sheaves now, and we package them in this class, which is called the spectral class of the mixed-Hodge module with this finite order automorphism. So what we do, we take the de Rham complex of these eigen modules of the underlying D module for the mixed-Hodge module. We take their graded pieces. I said these are complexes with coherent cohomology. So their Grothendieck class lands in the Grothendieck group of coherent sheaves. You apply the Todt class transformation on this. So this is this Baum-Fulton-McPherson Todt class transformation. This gives us some homology class. And then you correct this by some power of this variable t, and this power is exactly like in the definition of the Hodge spectrum. So P is the same as the P from GER P or GER minus P, and L of lambda is just a logarithm of lambda in 0, 1. Right, so the exponential of 2 pi I times this L of lambda is lambda. So if X is a point, mixed-Hodge modules over a point are just mixed-Hodge structures and the graded pieces of the RAM are just the cohomologies of that, sorry, are just the graded pieces of the Hoche filtration on that mixed structure. The tot class over a point is just the identity. So what you get here is just a definition of the Hoche spectrum, like, for example, Saito uses it when he proves this timbering conjecture. Okay, so this is a definition in the smooth case for a mixed Hoche module. In the singular case, the same definition applies using local embeddings into smooth varieties, because these graded pieces of the DRAM do not depend on these embeddings. And then you can extend this to complexes by just applying this definition up here to each cohomology object of the complex. So each cohomology object of a complex of mixed Hoche modules is itself a mixed Hoche module, and you apply the definition that I gave you up here, though you may be in the singular case, so you need to use these local embeddings. So this definition may seem a bit complicated, but in the end, what it does, it just packages the graded pieces of the Hoche filtration on the DRAM, and I want into a polynomial, and I want to value this in homology, so I move it to homology by the tot class transformation. So this is a classical transformation of Bauernfurt and McPherson, which appeared in this singular Riemann-Roch theorem. All right, so now we have a transformation which takes as an input a mixed Hoche module with a finite order automorphism on it, and it spits out a polynomial with rational Laurent polynomial with fractional exponents, but whose coefficients are homology classes. Okay, so the best example of such a thing, of such a mixed Hoche module with a finite order automorphism, comes from vanishing cycles. So this is, again, something classical from Deligne, which I'm going to put on the next slide. In the case of hypersurfaces, so let's say I have a function defined, a regular function defined on a smooth variety. It gives us a hypersurface by taking its zero set. And let's say the dimension of the hypersurface is d sub x. Okay. Then Deligne constructed a vanishing cycle functor. Here on the right, I have the picture of the Milnor fibration of a singularity, right? So you have your Milnor ball. I drew it as a ball, not as a tube. You have your singularity here, x, and a small disk downstairs, and above a general point in the puncture disk, you have your Milnor fibration. Down here, I don't know if you see this, but there is something in red. These are the vanishing cycles. Now, this is the local picture, and this was sheafified to a complex of sheaves, which is called the vanishing cycles of F. And this is defined here. So the vanishing cycle of F, the vanishing complex of F, is in fact obtained from a functor defined on derived categories of constructible sheaves. Don't worry too much about this. But it is a complex of sheaves. If you take the cohomology objects and the stalks at the point, at the singular point, you recover exactly the reduced cohomology of the Milnor fiber. So in this sense, you're sheafifying this local information into a global object, into a constructible complex. Yeah. And now on the right hand side, of course, you have the Milnor monodromy. In fact, this complex comes endowed with a monodromy automorphism itself, so that this isomorphism is compatible with the two monodromies. Now, the monodromy, of course, is not a finite order. So if you want something locally finite, maybe or finite, you take the semi-simple part of monodromy. And in fact, this is what we do. And this is how you create one of these. Maybe I should say this also leads to mixed Hoche modules, and this is what Saito showed. So that's what allows us to look at this complex as a monodromic complex of mixed Hoche modules and apply the previous definition to it when we endow it with the semi-simple part of the monodromy. All right, but let me maybe give you one example here, since I mentioned this constant, this vanishing complex of the constant sheaf. So I said that there is a lift. There is again a cohomological shift to get to preserve mixed-source modules, but there is a lift of this functor by Saito. And here is one example. So I'm interested, again, up to a cohomological shift of vanishing cycles of the constant sheaf, if you like, on the ambient space. This is also an object in Saito's mixed-source module theory. And what is this? Again, up to a shift, I said mixed-source modules have a D-module part, have a perverse sheaf part, and some compatibilities with the Riemann-Hilbert correspondence. So for this constant Hodge module, again, up to a shift, the D module is just a structure sheaf with the stupid filtration, with the, well, trivial filtration. The graded parts are all 0, except in degree 0, of course. Then the perverse sheaf is just the classical constant sheaf shifted by the complex dimension. So this is just, since Y is smooth, you get the perverse sheaf here. These two guys are related by the classical Riemann-Hilbert correspondence if you complexify the perverse sheaf. And then there are weights on both D module and perverse sheaf, and the Riemann-Hilbert is supposed to, the correspondence is supposed to preserve these weights. But in this case, all weights are, I mean, the graded pieces are all 0 except in one dimension. So this object has weight equal to the dimension of the ambient. So this is a mixed-source module. You apply this functor of Saito to it, you get the mixed-source module on X with the monodromy automorphism. Take the semi-simple part, and then you can create now a monodromic object, just like we had previously as an input for the spectral Hirzebruch classes. Applying the definition of spectral Hirzebruch classes to this particular object gives us what we called the spectral Hirzebruch-Milnor classes. Why Hirzebruch-Milnor? What's the story with Milnor here? Is that it's a subtop generalization of the Milnor number, if you like. So for the special choice of the parameter T, if your hypersurface is only one isolated singularity, then this class reduces up to a sign to the Milnor number. So for people who like Chern classes, this would be, if I specialize the parameter T to 1, you just get the Milnor class of the hypersurface that many people in Brazil actually study, right? So this is the Lins-Milnor class. Well, not the Lins-Milnor class, it's the Lins Chern class adapted to the hypersurface situation by subtracting this this Fulton class. All right, so now I have a class, homology class, and you notice here that I'm not writing the homology of X, but I'm writing the homology of the singularities of X. And this is done because the vanishing cycles are supported on the singular locus. So in fact, these classes detect singularities. Of course, if you have no singularities, these classes are 0, but otherwise, the fundamental class of the singular locus comes into the calculation of the class we define here. All right, so now relations to our notions of singularities, they're already observed, as I said, in this first work that we had with Saito and Schurman, and later on with Yang. This class that I define here for hypersurfaces already detects, first in the first work with Saito and Schurman, it detects Dubois and rational singularities. Then in the work with Saito and Yang, we show that this also detects higher notions of such singularities. And it also detects jumping coefficients of multiplier ideals and higher versions of such for the hypersurface. So this was all done already as of, I don't know, a few years ago. And this is, maybe some of you saw me giving talks about this. So many of you are very young. So, but anyway, so this is classical stuff. So now I want to move to the new story, to local complete intersections. So first I want to define characteristic classes for local complete intersections, and these are, of course, much more involved, but they use, in some sense, the definition I just gave you of Hirzebruch-Milnor classes. So I just need to create the right hypersurface to define the Hirzebruch-Milnor classes for, and this is given through a deformation to normal cone. So this is a classical construction which deforms the embedding of X in the ambient space Y. So this is our local complete intersection in the smooth ambient variety. It deforms it to the inclusion of X into as the zero section of the normal cone of X in Y. So LCIs, they have, the normal cone is actually a bundle, and X is the zero section in that normal bundle. And the inclusion of X in Y deforms, and this appears, for example, classically in, for example, Fulton's book on intersection theory describes this nicely. You deform this embedding of X and Y into the embedding of X into the normal cone of X in Y. And in fact, there is a projection from this. This is just a blow-up, but there is a projection to the complex line, so that the zero section is exactly the normal cone, and the general section is just the ambient variety Y. So what we're doing here, I'm creating a family of this Y, the variety I started with, the smooth variety. I started with the ambient with X sitting inside of it. And as I degenerate the parameter T towards 0, I just get the embedding of X into the normal cone of X in Y. But now I have a hypersurface, right? Except it's not X, but it's a related space. It's the normal cone of X. So I can take the vanishing cycle complex to the semi-simple part of monodromy for this hypersurface defined by H. Define the Hirzebruch-Milnor class there. I end up with a homology class with some Laurent polynomial coefficients on this normal cone. And to move down to X to the base, all I have to do is to apply the Giesen homomorphism. So in fact, this is the definition that we came up with. So if you take S the zero section, so the embedding of X as the zero section in the normal cone, as I said, you first take this spectral class, or if you like, the Hirzebruch-Milnor class for the cone. So this was defined as a spectral class of vanishing cycles of this deformation H to the normal cone. You apply it to the ambient constant Hodge on this deformation normal cone. I should say this is not smooth anymore. This causes some trouble, but it's still a rational, it's still a local complete intersection itself. So we end up with the homology class on the cone, and then you use the Giesen homomorphism to map down to the base. So this is the Giesen homomorphism here. So what we end up with is now going to be a homology class on the base X. In fact, it's supported also on the singular locus with these Laurent polynomial coefficients. All right, so so this is what I'm saying. It's supported on the singular locus just because this one is supported also on the singular locus on the cone. So if you think, for example, of a complete intersection, this cone is a trivial bundle, and the support is going to be exactly of this red class here, of the spectral class upstairs on the cone. The support is going to be the singular locus times the affine space, which is affine space of dimension R. And then when I use Giesen, I move exactly to the singular locus. All right, so here is a little proposition which says this classes also detect, in fact, they are very good at detecting the singularities of the local complete intersection. If you have a smooth local complete intersection, what you get is, of course, a zero class, because and the support was the singular locus. So if I have no singularities, then the class is zero. But as I was saying, in the case of hypersurfaces, if you have a singular local complete intersection, then the coefficient of the fundamental class of the singular locus in this characteristic class is non-zero. So remember, these classes are, if you like, Laurent polynomials with fractional powers whose coefficients are in homology of this singular locus, and there is the top piece there coming from the fundamental class, and that's non-zero if your LCI is singular. So this says that this class is indeed detects singularities. All right, so now what I want to do is to relate them more precisely to higher singularities. And well, maybe let me give you more examples first. So since they may seem a bit mysterious still. So let's say our LCI, I told you what happens in the smooth case. Let's say now that we have only one isolated singularity, let's call it little x. Then this class reduces up to some power of 1 minus t to the Hodge spectrum of the local complete intersection of this point x. And this is the notion that was introduced by Dimka, Maisonov, and Saito. So this is a Hodge spectrum for a local complete intersection. It goes through the deformation of the normal cone. So you have this vanishing cycle complex for the deformation, the normal cone projection. Take a stock of it and take the cohomology. So this amounts to calculating the cohomology of the minor fiber of H at this point C in a general, this C is a general point in the fiber over little x, the fiber of the cone over little x. Now this is a little bit more complicated, but in fact it gives you exactly the same situation as in the case of hypersurfaces, where I said that this characteristic classes that we introduce for hypersurfaces, the spectral Hirzebruch minor classes, are supposed to give you back the Hodge spectrum of the minor fiber of the singularity. So this is the local complete intersection version of that. The only, change is that this spectrum is now more involved to define. There is a whole paper about it by Dimka, Saito, and Maisonov. All right. And then local complete intersections includes the special case hypersurfaces. So what happens if I work with a hypersurface? I gave you two notions of characteristic classes, one given directly in terms of the vanishing cycles of the hypersurface, and the other one given in terms of the vanishing cycles that you get for the deformation of the normal cone. And in fact, the two notions that you get differ only by a power of 1 minus t. So this is all results that I discussed today for the left-hand side reprove the results we got previously for the right-hand side in the case of a hypersurface. All right, so maybe I should get to the main results and maybe, yes, tell you how these characteristic classes come into the study of higher Dubois and higher rational singularities. So main ingredients, so the same story. I have a LCI subvariety in a smooth variety Y. Codimension is R. Main ingredients for formulating the results are these Bernstein-Sato polynomials. You can do this for an LCI using this deformation, the normal cone. This is a generalization of the classical Bernstein-Sato polynomial. Then the notion of minimal exponent has been extended to local complete intersection subvarieties by Chen, Dirks, Mustazzo, Olano, and then Dirks. The initial definition goes through another hypersurface one can build out of the initial of the defining locally defined functions for x, but later on it was shown that by Dirks that you can actually define the minimal exponent just like in the case of hypersurfaces is the negative of the largest root of what's called the normalized Bernstein-Sato polynomial. So it is known that this s being the variable, s plus r, the codimension divides the Bernstein-Sato polynomial. So you divide by this s plus r, what you get is what's called the reduced Bernstein-Sato polynomial, and the negative of its largest root is the minimal exponent. This is a refinement of the low canonical threshold, just like in the case of hypersurfaces. In fact, the low canonical threshold is the minimum between the codimension of the LCI and the minimal exponent. And this is what I was saying earlier, that you can detect K Dubois and K rationality. In fact, you can completely characterize these notions by the minimal exponent. So K Dubois is equivalent to the minimal exponent being at least K plus R, K being this K from K Dubois and R being the codimension, and K rationality is the same sort of statement but with strict inequality. So now you see here, I gave you this example for this Briscorn type singularities for hypersurfaces. that really amounts to saying that this minimal exponent was the sum of 1 over the exponents. Okay. All right. So, of course, there is another ingredient here which I don't put on the slide, which is very technical and much more complicated. I already mentioned this word. This is called the V-filtration. You can do this also in the local complete intersection case, but it is much more complicated. So I decided to leave this out. So let's state the main results now. So let's assume that we work at least with, we have a technical assumption, but this is nothing to be worried about, because if we want to study higher singularities, well, it would be good to at least have Dubois if we want to have higher Dubois. So I told you these classes we defined are Laurent polynomials with fractional powers in the variable t and homology coefficients. So the homology of the singular locus is coefficients. So let us use this notation for the coefficient of t to alpha for alpha a rational number. So I'm looking at the homology coefficient in the singular set of x sitting next to t to alpha. Okay, so then these are 0 under our assumption. These coefficients of t to the alpha are 0 for alpha greater than something depending on the dimension of the ambient, the codimension of the LCI, and the minimal exponent. And this can be made into an if and only if the singular locus is projective, for example, if x is projective. Okay? So this is already some sort of characterization of vanishing of characteristic classes in terms of the minimal exponent, or if you like, you detect the minimal exponent from the vanishing of characteristic classes. Let me state another result, and then I will relate this to higher singularities, because those are the most suggestive statements that you can see. So I have two results here, two main results, A and B, which relate the vanishing of various species of this spectral minimal Hirzebruch class in terms of the minimal exponent. And again, these are if and only if conditions, if and only if statements, if the singular locus is projective. So there are two sorts, towards the top end of the powers of t and towards the bottom end. And let's try to make now use of k-Dubois and k-rationality description in terms of the minimal exponent. So these two results will have now two consequences. So one is a description of k-Dubois in terms of vanishing of these characteristic classes, the pieces of the spectral classes, in a certain range, depending on the dimension of the ambient space and the k that we care about here. And there is something similar for k-rational. And you see now, for example, since there was this question about how to move from, so k-rational implies k-Dubois, how to move from k-Dubois to k-rational. You see, I need an extra vanishing. I need the vanishing of this class also in degree dimension of y minus k, and this is again detected by this IC complex. And the Commerce implications hold if the singular locus is projective under our working assumption that the local canonical threshold is greater than the codimension minus 1. So, of course, for hypersurfaces, this is a no condition. This is the local canonical threshold is greater than 0. And but for complete intersections, we need to impose something like this. Okay, so this is one description of k-rationality and k-Dubois in terms of vanishing of pieces of this spectral minimal Hirzebruch class in a range towards the top. And now I have a similar description for vanishing in the bottom range. So k-rationality and k-Dubois implies, and it's if and only if the singular locus is projective again, implies is vanishing in a range below a certain range depending on k, right? So this is the description of higher singularities in terms of the characteristic classes. And let me conclude with a bunch of remarks. So first, as I said, these classes, in the case of isolated singularities, they reduce to this Hodge spectrum of Dimka, Saito, and Maisonneuve. So in that case, of course, the singular locus is projective if you have just isolated singularities. The conditions I gave you on the previous slide are necessary and sufficient for k rationality and k Dubois, and you can express them now in terms of vanishing of spectral numbers, right? So the coefficients of the Hodge spectrum. And then in the case of hypersurfaces, I mentioned that these things were done before and are in fact they're easier to deal with. So the case k is equal to 0 for the classical rational and Dubois singularities through these characteristic classes was already discussed in this paper we have with Saito and Schurman, and this generalized result of Ishii for isolated singularities. And then for higher singularities, this result was obtained by myself and Yang, and then Saito contributed to a more general statement. Finally, you may wonder why I want this projectivity into play of the singular locus to get if and only if condition. Why not compactness? And there is a weird example coming from Hironaka that says that you cannot replace projectivity by compactness. In fact, you don't get the converse statement if you just assume compactness. You need projectivity. This is a very special example, some sort of pathology. But you also cannot admit compactness completely because we work with Chow groups, right? And Chow groups of affine varieties are usually small. So if you want to actually get meaningful geometry, you need to have some substance in these Chow groups, and this is where compactness comes in. And I think my time is up, so I thank you for your attention.